Hi everybody, I hope this video finds you well. In today's video, which will be our last content video of our term, we'll be taking a look at section 9.5 from your textbook, which investigates how to deal with a defective coefficient matrix when solving a system of linear differential equations. Before we get into the content of this video, the general idea here is that when we have a defective coefficient matrix, we basically are in a situation where we don't have enough linearly independent eigenvectors. So what we're going to be learning about is a concept called a generalized eigenvector, which extends the concept of a normal eigenvector a little bit further, which allows us to generate enough linearly independent solutions to form the basis for our solution space. Now, in this discussion, generalized eigenvectors are something that if you guys were taking like a full class in linear algebra, you would investigate a lot further because generalized eigenvectors connect to a lot of more advanced linear algebra topics, specifically one of the most famous ones, which is a investigation of matrices through what's called Jordan canonical forms. Your textbook actually does investigate some of those things. It's just not part of our sort of course objectives. So we're not really going into those sections in a lot of detail. So that means that in this section 9.5, we're just going to introduce the concept of a generalized eigenvector, talk a little bit about it, then state a theorem without proof that actually explains how these generalized eigenvectors allow us to solve these defective constant coefficient systems of differential equations, and then just look at some examples. So this does wrap up sort of what we've been doing, which is learning how to extend what we learned about for solving higher order linear differential equations to systems of differential equations. However, some of the sort of theoretical aspects of this section we sort of have to skip over just because we don't have quite enough of the linear algebra to do everything in full depth here. So let's get into some of the definitions and the main idea. So we're going to let A be a square n by n matrix with an eigenvalue lambda. We're going to define what's called a generalized eigenvector of order k for this eigenvalue. And we're going to say that this generalized eigenvector is a vector v such that a minus lambda in raised to the kth. So a minus lambda in is a matrix. So we're multiplying that matrix with itself k times. Then times the vector v equals 0. And as a second component of this definition, a minus lambda in to the I times v never equals 0 for any power less than k. In other words, what this is saying is something is a generalized eigenvector of order k if the first exponential of a minus lambda in that eliminates v is equal to k. If all the previous exponents do not cause this to become the 0 vector, but the kth one does, then we call that a generalized eigenvector of order k. You guys should make a note here that a standard eigenvector, just a normal eigenvector, is the same as a generalized eigenvector of order 1, right? So the concept that we've investigated in most of our course back when we first started doing this in chapter 7 and back in what we were doing in section 9.4, normal eigenvectors are just a special case of this for order 1, so where a minus lambda I to the 1 times v is equal to 0. That's how we actually solve for eigenvectors. And now we're just extending that concept a little further. Okay, so now we know what a generalized eigenvector is going to be defined as. We don't quite know yet how we would calculate these easily, but we'll see that as we start our examples. However, we have to talk a little bit more about if we can find one of order k, we can actually find eigenvectors of any lower order. So there's this little statement here. If v is a generalized eigenvector of order k for eigenvalue lambda, then the vector created by doing a single multiplication of a minus lambda in times v will be a generalized eigenvector of order k minus 1. So in other words, of order 1 less than the original generalized eigenvector. And this statement here, it might seem sort of mysterious, but it actually is pretty clear right off the bat, right? If we know that you have this generalized eigenvector of order k, that means a minus lambda in to the k times v is equal to 0. If you think about the vector instead of as v, but as a minus lambda in v, well, then you would only need k minus 1 iterations of a minus lambda in to get to 0 because you already have one here. So if we multiply a generalized eigenvector by a minus lambda I n, what we get is another generalized eigenvector, but of a lesser order. This means that we can get this sort of idea of a chain of generalized eigenvectors. If we have an eigenvector that's order 3, then we can get one that's order 2, and then we can get one that's order 1. If we have an eigenvector that's order 5, then we can get one that's order 4, order 3, order 2, order 1. And remember that order 1 is the same as just a normal eigenvector. So to summarize that sort of intuition there, we should say that this gives us the idea of a chain of generalized eigenvectors that will always end at a standard eigenvector. Generalized eigenvectors overall allow us to handle defective constant coefficient matrices, those that don't have enough linearly independent eigenvectors. If we can't find n linearly independent eigenvectors, we can't find our n-dimensional basis for our solution space. But generalized eigenvectors allow us to deal with that. What we're going to do next is state a theorem that explains how these generalized eigenvectors allow us to find those extra missing vector functions that we need for our solution space. So let's go ahead and take a look at that theorem. All right, so this theorem, it's a little bit tricky here because it's got a lot of setup, but we'll go through and talk about each piece, and it'll be a lot more clear once we get into our examples. So let's suppose that lambda is an eigenvalue of matrix A that has less linearly independent eigenvectors than its multiplicity. Remember, back when we first defined eigenvalues and multiplicities and dimensions of eigenspaces and all that stuff, we said that as soon as one eigenvalue has less linearly independent eigenvectors than its multiplicity, the entire matrix is going to be defective because other eigenvalues can't make up for the missing linearly independent eigenvectors. So, by saying this, if we're going to suppose that we have just one eigenvalue that has less linearly independent eigenvectors, that it guarantees our matrix is defective. Okay, so now we're going to suppose that V sub k is a generalized eigenvector for lambda of order k. And we're going to assume that it has this eigenvector chain, vk minus 1, all the way down to v1, which would be a standard eigenvector. Now, how would we determine this chain? Well, if we know v sub k, then v sub k minus 1 would be a minus lambda I times v sub k. If we multiply by a minus lambda I once, we would get v sub k. To get the next one, v sub k minus 2, then we would do a minus lambda I times v sub k minus 1, and so on. And again, that's why we reference it as an eigenvector chain, or sometimes you'll hear it as a cycle. But basically what we're saying is if we can find the highest order one, then successive multiplications by a minus lambda I will give us the full chain, and each of these will be of one order less than that first one. All right. Then we get the following k linearly independent solutions. And notice that this k matches the order of the generalized eigenvector. So the first solution, x1 of t, is e lambda t v1. This guy right here is nothing new. This is the solution that we already use when things are non-defective. It's just saying we do e lambda t times v1, where v1 is the standard eigenvector. So this guy is the normal part. Everything else here is the sort of modifications we need to do because we have generalized eigenvectors. So x2 of t would be e lambda t v2 plus t v1. So we use the second order eigenvector plus t times the first order or standard eigenvector. Then x3 of t would be e lambda t v3 plus t v2 plus 1 over 2 factorial. We could just say 1/2, but the factorial shows us the pattern. T squared v1. And that'll continue all the way down until we get to xkt, which will be e lambda t vk, which is our highest order generalized eigenvector, plus tvk minus 1 plus 1 over k minus 1 factorial, t to the k minus 1, v1 being the original eigenvector again. Now, like I said, this guy right here is so close to being within our sort of range of being able to prove. It's not a terrible proof here, but unfortunately we're just missing a couple extra sort of pieces of knowledge about generalized eigenvectors and that thing I sort of mentioned, the Jordan canonical form, which if we had had a full class in linear algebra, we would be able to sort of do this and really see exactly why this sort of strange pattern emerges. But unfortunately, we're going to have to state this thing without proof and sort of move on from here. However, I will make one comment here. This pattern, as you guys are seeing, should not seem super unfamiliar. These coefficients here, they're really sort of related to the fact that if we take multiple derivatives of these things, what's happening is that each successive derivative is sort of leading back to a previous step. And that's why we're getting that factorial in there. And that is part of the sort of trick to the proof. But again, we're not going to go through the full proof here. Instead, we're going to go ahead and move on to taking a look at a couple examples. So let's hop into our examples and make sure that we can actually understand what this theorem is sort of stating here. So let's go ahead and jump into those. So our first example, we're going to try to find the general solution to x1 prime equals 2x1 minus x2 plus x3, x2 prime equals x1 plus 4x2 plus 2x3, x3 prime equals 3x3. So at the beginning, of course, we have no idea if this is going to be defective or non-defective. We just have to start as normal by changing it into a vector differential equation, trying to find the eigenvalues. So let's go ahead and rewrite this. This is x prime of t equals, and our a here, we don't need to write a, we want to actually write out what it looks like. 2 minus 1, 1, 1, 4, 2, 0, 0, 3, and then times x of t. So we need to find the eigenvalues for this guy here. So let's go ahead and do that. So we'll take the determinant, 2 minus lambda, minus 1, 1, 1, 4 minus lambda, 2, 0, 0, 3 minus lambda, and then we're going to set that determinant equal to 0. So let's go ahead and take a look at what this is going to look like. Probably easiest to row expand along the bottom here. So we can get 3 minus lambda times the determinant, and of course we'll cross that out and look at the determinant of the resulting minor. So 2 minus lambda minus 1, 1, 4 minus lambda equals 0. And then we should be able to do that pretty quickly. 3 minus lambda. We multiply these guys together. Looks like we'd get lambda squared minus 6 lambda plus 8. And then subtract these guys, so we get plus 1. And looks like we'd get 3 minus lambda and lambda squared minus 6 lambda plus 9. And 3 minus lambda, and that looks like we get lambda minus 3 squared equals 0. And so it looks like we have lambda equals 3 as our only eigenvalue with multiplicity 3. Now, the fact that we have an eigenvalue here with multiplicity greater than 1 does not mean that this is automatically defective. But it does mean that it has the potential to be, because if this guy doesn't have 3 linearly independent eigenvectors, then we're going to have less linearly independent eigenvectors than the multiplicity, and it's going to be defective. So let's go ahead and take a look at what the eigenvectors look like here. So we'll pull this over here. All right. So we'll take and we'll look at the eigenvectors for lambda equals 3. So we've got to get our a minus lambda I, which is subtracting 3 off the diagonal. So we'll get minus 1, 1, 1, 1, 2, and 0, 0, 0. And we'll augment that with 0, 0, 0. So we can start to solve this pretty easily by doing row 2 and replacing row 2 with row 2 plus row 1. So we get minus 1, 1, and then 0. And then looks like we should get 0, 0, 3, 0, and then we already have 0, 0, 0 there. And that's good enough. That's close enough to row echelon that we should be comfortable here. We want to avoid parameterizing here and here. So I guess we would say, let's let A2 be W. All right. The bottom, or this middle equation, I guess, would give us 3A3 is 0. So we know that A3 is 0. And then we get negative A1 minus A2 plus A3 is 0, which I guess becomes negative A1 minus W equals 0. And A1 looks like it's going to be negative W. So our eigenvectors here have form negative W, W, 0. And right here, this tells us A is defective. How do we know that? Well, if we wanted a basis, we would have something like negative 1, 1, 0, which means that the eigenspace is dimension 1, which is less than the multiplicity. So this means A is defective. So A is defective. All right, that means we need to go hunt for some generalized eigenvectors. How many generalized eigenvectors do we need? Well, we only got one linearly independent eigenvector from lambda equals 3, so we're going to need a couple, 2 generalized eigenvectors. So let's think about the next order. This guy is an eigenvector of order 1, so let's think about eigenvectors of order 2. So let's bring that onto the next page here. So now we want to consider eigenvectors of order 2. So remember, that would mean that we want a minus 3i squared times v to be equal to 0. Right? So that's what we need to consider. Now, of course, to be an eigenvector of order 2, we would need this to be true, and we would need a minus 3i times v to not be 0. But we can worry about that later. Let's just start by finding the potential eigenvectors of order 2. So we probably first need to know what a minus 3 lambda I squared is. So a minus 3 I squared is, well, we already did a minus 3i. It's this thing right here. So we just need to multiply that with itself. So we got negative 1, what is that, 1, and then 1, 1, 2, and then 0, 0, 0, and then times itself, negative 1, 1, 1, 1, 1, 2, and then 0, 0. So let's go ahead and multiply that out. So we'll take our row times our column, which looks like that's going to be negative 1 and negative 1, so that's 1, and then negative 1 and 1, that's negative 1, so that's going to be 0. And then this times this is going to give us 1 and negative 1, so 0. And then this times this looks like it's going to give us negative 3. Then this times this looks like that's going to be 0, then 0, and then 2, 3. Yep, okay. And then finally we'll get 0, 0, 0. So there we go. There is our a minus 3i squared. Now we want to solve this equal to 0, so we can augment that with 0. So 0, 0, minus 3, 0, 0, 3, 0, 0, 0, augmented with 0, 0, 0. Well, we can just simply do R2 and replace it with R2 plus R1. And looks like we should get 0, 0, minus 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay, nice and easy. Now we want to avoid parameterizing here. So I guess we can go ahead and let A1 be W and A2, I don't know, let's go ahead and just call it S. You know what, since we use W there, let's use Z for that guy. All right, W and Z. All right, now this equation tells us that negative 3A3 is supposed to be 0, so A3 is 0. So the potential order 2 eigenvectors are of the form W, Z, and 0. Now, we might say, perfect, right? We needed 2 more sort of eigenvectors that on top of the first one that we had already found, right? And we could say, okay, we can use the W and the Z. But notice I carefully said potential order 2s. Well, the reason that it's so important to say potential is that notice that if we look at some of these, right, some of this has overlap with this here, right? If I choose W to be equal to negative Z, there's overlap here with this here. So, in other words, what we're saying is there can really only be one order 2 eigenvector. We can also know that by that idea of chaining. If we try to claim that there's 2 separate order 2 eigenvectors, they both have to chain back to order 1s. But there's only one order 1. So there can only be one order 2, which chains to that order 1. So some of these in here actually overlap with the original order 1 eigenvectors, so it's still not going to be enough. So what does that mean if we need 3 things overall? We need to go find an order 3 eigenvector. So let's go a step further. And let's talk about eigenvectors of order 3. So let's consider EV of order 3. So now we want to consider a minus lambda I cubed v equals 0. So we first want to determine that a minus lambda I cubed. Well, we can do that sort of sneakily. We can grab that this was what we had when we squared it. So let's just grab that guy. And we'll paste that guy right in there. And then we can just multiply it by a minus lambda I, which we had here. So we can grab one of these. We just need one of them. And we can multiply those together. So that'll give us a minus lambda I cubed. Okay, so let's do that. This row times this column, that's going to be 0, and then 0, and then 0, and then 0, 0, 0, and then 0, 0, 0. So a minus lambda I cubed is equal to the 0 matrix, which means V could be anything. Sort of. It means anything could be potentially an eigenvector of order 3. But remember, we want to avoid things that are eigenvectors of lower order, because if you're an eigenvector of lower order, you can't also be an eigenvector of higher order. So how do we find our eigenvector of order 3? Well, we just choose anything that avoids this form, so anything that's WZ0, and anything that avoids this form, negative WW0. Well, notice that both this guy has that 0 there, and this guy has the 0 there, so let's just be really safe. Let's choose 0, 0, 1. That certainly isn't of the form. So we want to avoid EV of order 1, EV of order 2. So let's choose V3, our generalized eigenvector of order 3, to be 0, 0, 1. Now we can go ahead and build our chain. How do we do that? Well, V2 has got to be a minus lambda I, so a minus 3I, times 0, 0, 1. Well, what is a minus 3I? It's our matrix up there. It's minus 1, minus 1, 1, 1, 1, 2, 0, 0, 0, and let's multiply that with 0, 0, 1. Okay, what do we get here? Well, we get this times this. That gives us a 1. Then we get this times this, which gives us a 2. And then we get this times this, which gives us a 0. So we're claiming that if we choose this to be our order 3, this is our order 2. Does this fit the format for order 2s? Yep, WZ0, and we're saying W should be 1, Z should be 2. There we go. How do we find V1? Well, V1 should be a minus 3I times V2, which is 1, 2, 0. So we're going to do minus 1, minus 1, 1, 1, 1, 2, 0, 0, 0, times 1, 2, 0. So let's see what we get then. This times this, that's going to give us negative 3. This times this, that's going to give us positive 3. And this times this is going to give us 0. Does that fit the form that's supposed to be for a first order eigenvector? Well, we look back over here, negative WW0, and that is exactly what we got, negative 3, 3, 0. So that tells us that this is the chain we can use. Would we get a different chain if we chose a different V3? Absolutely. But it would still be an equivalent answer, right? So you can choose anything here as long as you don't choose something of the order 1 or order 2, and then you have to get the resulting chain from that. So what does this tell us for our solution then? So this tells us that our general solution, which we can put right here, our general solution is going to be x of t is C1 e to the 3t, because our lambda was 3. And this is our order 1 eigenvector, so we use that first, negative 3, 3, 0. And then I'm going to write it sort of in the form that the theorem looks like. So then C2, and we'll have e to the 3t, and then parentheses. Now we use the order 2, 1, 2, 0, plus t times the order 1, which is going to be negative 3, 3, 0. And then plus C3 e to the 3t. Now we use the order 3, which was 0, 0, 1. So 0, 0, 1 plus t times the order 2, which is 1, 2, 0, plus 1/2 t squared times the order 3, or sorry, the order 1 minus 3, 3, 0. And there we go. There's our general solution. Only one linearly independent eigenvector, but we're able to build two more solutions using these generalized eigenvectors. Okay. Now, before we get to our next example, something I want you guys to sort of recognize here is since we only had one order 1 eigenvector and we needed 3, it had to be a 3 chain. It had to be. There was no other option because we only had one order 1, so we could only have one order 2, so we could only have one order 3, and that was going to be it because we needed 3 eigenvectors. The next two examples we're going to do, we're going to see that there can sometimes be other options, and we won't know which one until we sort of work through it. So let's get to those other examples. So for our next example, I think we accidentally added some extra pages there. All right, just ignore those. All right, there we go. Now we're going to try this guy here. We're going to try to find the general solution to x prime t equals axt, with A being this matrix 4, 1, 0, 0, 0, 4, 0, 0, 0, 0, 4, 1, 0, 0, 4. So again, we're going to start by finding the eigenvalues. So we need to find lambda. Let's go ahead and do that by taking the determinant of a minus lambda I, so 4 minus lambda 1, 0, 0, 0, 4 minus lambda 0, 0, 0, 0, 4 minus lambda 1, and 0, 0, 0, 4 minus lambda. And let's set that determinant equal to 0. This guy is nice and easy. It's upper triangular, so this is just 4 minus lambda to the 4th equals 0. So we get lambda equals 4, multiplicity 4. So potentially could be defective here because we have multiplicity greater than 1. This guy is going to need 4 linearly independent eigenvectors to be non-defective. If it has anything less, it'll be defective. All right, so let's go ahead and find our eigenvectors. So eigenvectors, and now you guys can think about that as order 1, really. So we need to do a minus 4i, so we have to take 4 off the diagonal, so 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, and then 0, 0, 0, 0. Okay, so we would avoid parameterizing here and here. This guy's already in row echelon form. So I guess we can say that A1 is going to be W, and A3 is going to be Z here. Yep, that looks good. So this equation here tells us that A4 is supposed to be 0. And this equation up here actually tells us that A2 is supposed to be 0. So that pretty much does it for us because we have these guys parameterized and these guys are 0. So we know the eigenvector. Eigenvectors are of form W0, Z0. So there we go. That's what the eigenvectors are a form of. Now, what does this tell us? Well, this immediately tells us that we're in a defective situation again because the eigenvectors have 2 free parameters. So the eigenspace is dimension 2, which is less than the multiplicity here. Now, what does this tell us as the potential for generalized eigenvectors? Well, what you guys should be sort of thinking here is since we have 2 standard eigenvectors, we could have a 3 chain and a 1 chain. That would give us 4 linearly independent eigenvectors. Or we could have a 2 chain, 2 chain. In other words, we have 2 separate second order eigenvectors, each of which that chain to one of our standard eigenvectors. Either of these are possibilities. Unlike in the previous example where we only could have a 3 chain because we only had 1 standard eigenvector. This time we have 2 separate types of eigenvectors, so we could have a 3 chain and a 1 chain, or a 2 chain and a 2 chain. All right, let's figure out which one it's going to be by taking a look at what types of order 2 eigenvectors we have. So we'll give ourselves another page here. So now we want to consider EV of order 2. So we want to look at a minus 4I squared times v equals 0. So let's look at what a minus 4I squared even is. A minus 4I was 0, 1, 0, 0, then 0, 0, 0, 0, then 0, 0, 0, 1, and then 0, 0, 0, 0. So let's multiply that then with 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay? All right, so let's multiply that out. This row times this column, that's going to be 0. This row times this column, going to be 0, then 0, then 0. Then we have a 0 row, so it's going to be a 0 row. Then this guy times each of these is always going to be 0. So 0, 0, 0, 0. And then another 0 row, 0, 0, 0. When you guys are doing these multiplications, a good trick is any 0 row in the first matrix becomes a 0 row here. Any 0 column in the second matrix is going to become a 0 column here, and then you can just do the last couple ones. So this is the 0 matrix. So again, that means everything could potentially be an eigenvector of order 2, except the things that are already eigenvectors of order 1. So we should be able to choose 2 different things that are eigenvectors of order 2 as long as we avoid the eigenvectors of order 1. So we want to avoid eigenvectors of order 1. So let's choose V2, since we'll call it, we just need to avoid things that look like this. So why don't we choose something like 0, 1, 0, 0, and maybe 0, 0, 0, 1, things like that. So let's choose V2. We said we want to avoid, so 0, 1, 0, 0. That's definitely not an eigenvector of order 1. And let's also do U2 to be 0, 0. We just want to avoid that guy, so 0, 1. There we go. Now notice that these are definitely linearly independent from each other, and they're definitely not eigenvectors of order 1, so they will be eigenvectors of order 2. Now I'm saying VT and UT because we have 2 eigenvectors of order 2 this time. Now we do need to figure out which of these chain to. So we would then have V1 here be our a minus 4I times this. So let's figure out what that would look like. 0, 1, 0, 0. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, times 0, 1, 0, 0. And what are we going to get here? Well, this times this gives us 1, and then we have all 0 rows, so 0. And then we have this guy times this, which is going to be 0, and then 0. So this tells us that if we choose this as our order 2, this guy will chain to 1, 0, 0, 0, which is of this form. It's specifically when W is 1 and Z is 0. All right, now we pretty much know what U2 is going to chain to. It's going to have to chain to the other type, but let's just check that. For U1, we would get 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, times that 0, 0, 0, 1. And if we do that, this row times this is going to be 0, then 1, then 0. And there we go. So if we choose this guy, magically again, this will chain to the other type of eigenvector. All right, so what does our solution look like? Well, x of t then, let's start by using our V sort of chain here. So we'd have C1 e to the 4t, and then 1, 0, 0, 0, just the standard eigenvalue. Then we would continue that chain, C2, e to the 4t, parentheses. Now we use its order 2, but make sure you use the V, because we're on that chain right now. So 0, 1, 0, 0, plus t times the eigenvector, 1, 0, 0, 0. Okay, now that'll conclude the V chain. So now we'll move to the U chain. So plus C3, e to the 4t, And the u, that 1, is going to be 0, 0, 1, 0. So 0, 0, 1, 0. And then we continue that chain, C4, e to the 4t, parentheses. We use its order 2, which is this guy here, 0, 0, 0, 1. So 0, 0, 0, 1 plus t times the actual eigenvector, 0, 0, 1, 0. And there we go. So there's a 2 chain, there's a 2 chain, and together, those two chains, well, they give us our 4 linearly independent solutions. So we now have our basis, and we now know our general solution to this guy. All right, let's get to our very last example. All right, so we want to try to find the general solution to this crazy thing here, right? This matrix that is 1, 0, 0, 0, 0, 0, 4, 1, 0, 0, 0, 0, 4, 1, 0, 0, 0, 0, 4, 0, 0, 0, 0, 4. And when we do this example, we're going to make sure that we compare and contrast it to the previous one. So let's go ahead and determine the eigenvalues. So we need to take the determinant of 1 minus lambda, 0, 0, 0, 0, 0, 4 minus lambda, 1, 0, 0, 0, 0, 4 minus lambda, 1, 0, 0, 0, 0, 4 minus lambda, 0, and 0, 0, 0, 0, 4 minus lambda. We'll set that equal to 0. Oh, thank goodness this is upper triangular. It'd be horrendous if it wasn't, but you guys will notice most of the time these will be to make things a little bit easier. So we get something that looks like that, and it looks like we have a lambda equals 1 with multiplicity 1, and a lambda equals 4 with multiplicity 4. Again, this guy is our concern because it has a multiplicity higher than 1, so there's potential for this guy to be defective here. But let's start with the easier one. Let's think about the lambda equals 1. So we need to think about our eigenvectors for lambda equal 1. So let's subtract 1 off the diagonal, get 0, 0, 0, 0, 0, then 0, 3, 1, 0, 0, then 0, 0, 3, 1, 0, then 0, 0, 0, 3, 0, and then 0, 0, 0, 0, 3. And then we augment with 0, 0, 0, 0. Looks a little bit weird, but this guy is actually already in good form. We want to avoid parameterizing any of these guys. So I guess we can just go ahead and do A1 equal to W. So bottom equation tells us that 3A5 is equal to 0. So I guess that tells us A5 is 0. Then we get that 3A4 is equal to 0. So A4 is equal to 0. Then we get 3A3 plus A4 is equal to 0. But since A4 is equal to 0, we know that that means A3 is going to be equal to 0. And then finally, we get 3A2 plus A3 is 0. But since A3 is 0, that tells us A2 is going to be 0. All right, well, looks like everything's 0 here. So we get our eigenvectors are of form, well, W, 0, 0, 0, 0. Now, we've been doing all this stuff with these generalized eigenvectors. Are we going to have to do any of that with this? Well, no, because this has dimension 1, but this guy only had multiplicity 1, so everything's going to be good here. We're not going to look at any generalized eigenvectors for this lambda equals 1. This guy, if you want to say that one eigenvalue is non-defective, this eigenvalue is non-defective. Now, that doesn't mean the matrix is, because we have to look at this eigenvalue, but there's nothing weird that we have to do here. We've got everything that we need in terms of just its normal eigenvectors. So now let's think about the eigenvectors for lambda equals 4. So eigenvectors for lambda equals 4. So now we need to subtract 4 off the diagonal. So it looks like our top diagonal is going to be minus 3 and then 0, 0, 0, 0. And then looks like we should get 0, 0, 1, 0, 0. And then subtract the 4. So 0, 0, 0, 1, 0. And then subtract the 4. So 0, 0, 0, 0, 0. And then 0. And then bottom row, 0, 0, 0, 0, 0. So I think that looks good. Yep, absolutely. And augment that with 0, 0, 0, 0, 0. All right, looks a little bit weird, but again, let's think about this is actually already in row echelon form, so we just want to avoid parameterizing here, here, and here. So I guess we can let A2 be equal to W and A5 be equal to Z. So the equation should be pretty clear. A4 equal to 0, A3 equal to 0, and negative 3A1 equals 0. So yeah, A1 is 0 too. All right, so eigenvectors have form, well, 0, W, 0, 0, Z. Well, certainly these things are linearly independent from here, which we already knew because eigenvectors from different eigenvalues are automatically linearly independent, but there is a problem. This guy is dimension 2 and we are multiplicity 4. So we're going to be 2 eigenvectors short. What are the options for generalized eigenvectors? Well, since we have 2 eigenvectors of order 1, that could mean that it's going to be a 2 cycle and 2 cycle. So in other words, there's 2 order 2s and they each go to one of the order 1s. Or it could be that there's a 3 cycle and a 1 cycle. In other words, there's something that's order 3. So there's an order 3, then an order 2, and then an order 1, and then the other order 1 just sits by itself. Both of these are possibilities. We'll have to find out which one by examining the order 2s. So let's go ahead and talk about that. So let's talk about the eigenvectors of order 2. So let's consider a minus 4i squared of v equals 0. So what is a minus 4i squared? Well, a minus 4i was this thing, so we got to multiply that with itself. So it looks like we're taking minus 3, 0, 0, 0, 0, right? And then 0, 0, 1, 0, 0, 1, 0, 0. And then 0, 0, 0, 1, 0, so 0, 0, 0, 1, 0. And then all zeros. And then I think the bottom was also all zeros. Yep, all zeros. Okay, and we'll just make this easy so we don't have to rewrite it. We'll just copy that and paste it with itself. Okay, and let's multiply those out and let's see what we get. So this row times this column looks like we're going to get a 9 up there. And then everything else is going to be 0, 0, 0. Then this row times these things, this always chooses out the third element. So it looks like we're going to get 0, 0, 0, and then we'll get a 1. So it'll be 0, 0, 0, 1, and then 0. This guy already chooses out the fourth element. Fourth element is already 0, though. So it looks like we're going to get 0, 0, 0, 0. Excuse me. And then the bottom 2 rows are already 0 rows, so after multiplication, they'll also be 0 rows. Okay. So there we go. That's a minus 4i squared. So let's augment that with 0. Notice that this time this is not the 0 matrix, so that doesn't mean everything. So let's augment it. Okay, 9, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, augmented with 0, 0, 0, 0. Okay, we want to avoid parameterizing these guys. So I guess we can let x2 be w. It's not x2, we're calling them a here, aren't we? a2 be w, a3 be z, and I guess we can let a5 be y. Okay. Then, of course, it's very easy to see that this says that a4 is supposed to be 0, and we also get that 9a1 is supposed to be 0, so a1 is equal to 0. So these are, again, the potential EV of order 2 are going to be of form 0, W, Z, 0, Y. Okay. So does this mean that there are 3 dimensions worth of order 2 eigenvectors? Well, unfortunately not. If we go back and look, right, anything that is 0, W, 0, 0, Z, so here in the second component and in the fifth component are actually eigenvectors of the first order. So actually these are first order and these are first order. So that means we actually only got 1 order 2. Well, that means we need to look for order 3. So this tells us, since we can only find a single linearly independent EV of order 2, we need an EV of order 3. Now, there is a little bit of sort of a cheat for getting that eigenvector of order 3. At this point, we have 4 different linearly independent things. At this point, right, we know that something that is of form 1, 0, 0, 0, 0, that's an eigenvector from the first eigenvalue. We know that things 0, 1, 0, 0, 0, or 0, 0, 0, 0, 1 are eigenvectors from our second eigenvalue. We now also found something that of form 0, 0, 1, 0, 0 is going to be an eigenvector of order 2. If we just pick anything else, then we can determine that chain that is going to correspond here. So let's move on to our last page here. So we need to choose EV of order 3, avoid all other eigenvectors. So again, we want to avoid anything in the first component. Oh, sorry about that. Anything in the first component, anything in the second or fifth component. So no first, no second, no fifth, and no third. So we would only want something in the fourth component to be safe. So let's choose V3 equal to 0, 0, 0, 1, 0. Now, we need to figure out where this chains to. What are its options? Well, it might chain to 0, 1, 0, 0, or something like that. So 0W, 0, 0, 0. Or it could chain to something like 0, 0, 0, 0, something. So we have to determine which of these eigenvectors this chains to. Shouldn't be too hard to do that, though. V2 then is going to be our A minus 4i, so our minus 3, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, and then 2 0 rows down here. So that's our A minus 4i times this guy, 0, 0, 0, 1, 0. So let's see, this row times this column, that's going to be 0. This row times this column is going to be 0. Then this row times this column is going to be 1, and then 0, and then 0. So the V2 should be 0, 0, 1, 0, 0. Are we shocked? Not at all, because we said the potential EV of order 2 are of this form, but we said this and this are actually going to show up in the eigenvectors of order 1, so it had to just be here, and that's exactly what we just found. What's the V1 then? Well, V1 is going to be negative 3, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, times that guy, 0, 0, 1, 0, 0. And if we do that, row times column, that's going to be 0. Row times column is going to be 1, then 0, 0, 0. So it chains to 0, 1, 0, 0, 0, which is of this form. It's the W equals 1, Z equals 0 form. So there we go. So we're now ready to put all this together. So our general solution here, x of t, is C1. Let's start with the easy one. So back over here for eigenvalue lambda equals 1, we had this. So we can say C1 e to the t, and then a basis for that would be 1, 0, 0, 0. Right? And that's just by going back over here and choosing w to be 1, all these would be 0 then. So that's our first component there. Then plus C2. If we want, we can now start with this chain here. So C2 e to the 4t, and then 0, 1, 0, 0, 0. Then plus C3 e to the 4t. Move this chain along. Next one is 0, 0, 1, 0, 0 plus t times 0, 1, 0, 0, 0. And then final step of that chain, C4, e to the 4t. Order 3 was 0, 0, 0, 1, 0. So, parentheses, 0, 0, 0, 1, 0 plus t 0, 0, 1, 0, 0 plus 1/2 t squared 0, 1, 0, 0, 0. All right, are we done? Well, we actually have one more plus c5 e to the 4t. Got to go back and grab the other eigenvector that was not part of the chain. That would be the 0, 0, 0, 0, 1. So if we do that, we get c5 e to the 4t 0, 0, 0, 0, 1. And there we go. That linear combination, that horrible mess, is actually our general solution for that linear system of differential equations. That ends the content videos for our class. That ends our lectures. Well, I suppose, signing off.